Okay, good morning, everyone. Today we are going to talk about the last chapter of Book 4 Boy, which is chapter 49. We focus on the transition metals about the properties. So this chapter actually is not very difficult because we just understand some basic properties such as transition metal have color and they have a variable oxidation state and they have the catalytic properties. Okay, so and some important compound for transition metal. Later we are just focus on these mainly three properties. So what is the transition metal? Transition metal actually, if you find from the periodic table, is from period 4 to period 7. Okay, this block is filled up by 10 transition elements. Okay, and then we just call them transition metal. For this, actually in this part is a transition metal, right? In our syllabus we seldomly talk about this part, so you will use this chapter to focus more about the transition metal here. So the transition metal actually occupy from period 4 to period 7, between group 2 to group 3. Okay, and then the 10 elements from scandium and zinc that lie between calcium and gallium are all metals, we know, right? They form the first series of transition metals. So therefore here these parts all metals. Okay, now this is the properties that actually you can see they are shiny in appearance, so that's why they are in metals. Okay, electron in both the outermost shell and the next inner shell of most transition metal atom contribute to the sea of element, so that they can have a strong metallic bond. Okay, because the outermost shell of the electron can donate can become the sea of the element, so they can conduct electricity. So but for the main group, you can see for main group only the electron from the outermost shell. But for the transition metal, not only outermost shell and the next inner shell. Okay, so therefore two shell donate the electron, but in the main group element, main group metals, only the outermost shell electron contribute to the sea of the electron. This is the difference. Now you can see this is the scandium. These two donate electron. Okay, and then you can see they are bonding the melting point. Actually the melting point is variable. Okay? And then based on the melting point, you see vanadium is the highest melting point. The reason is, of course, the metallic bond is stronger. Why? Maybe the two outermost shell electrons donate to the sea of electron, and also these 11 electrons also contribute to the sea of electrons, so that the metallic bond is quite strong. But for manganese, you see manganese quite low. Like you can see, but for the next shell, there's a 13, but not all the 13 electrons contribute to the sea of the electron. So that's why the melting point, the metallic bond, is not that stronger. Okay, so therefore, the strength of the metallic bond depends on the electron. Alright, but for the transition metal, they don't have fixed number of electrons contribute to the sea of the electron. So sometimes actually there's a variable, and that's why they have the variable oxidation number. Now I don't go in detail. Okay, you can see. But for zinc, the melting point only 420. Why? Because for zinc, only the last electron will contribute to the seas of electron. You remember zinc, what is the charge? Zinc 2 plus. That is the reason. But for copper, you see outermost shell is 1, so therefore copper can be 2 Cu plus and Cu2 plus. Why 2 plus? Because one of the electron from 18 will donate to the sea of electron. Okay, so therefore here for iron, you can see iron is iron 2 plus lah, but iron, if you remember, they are iron 3 plus. So therefore, the 40 electron, one of the electron will donate the electron. So therefore, this is not necessary for transition metal. The concept is not like our main group elements. Okay. Generally speaking, high melting point. Okay, very high, higher than our main group. So you can see magnesium, sodium only below 1000 degrees Celsius. Zinc is a transition, but it has a lower melting point comparable to that main group. Zinc is very special. Zinc is not that higher melting point. Even zinc is the transition metal. Okay, but you can see from the table, zinc is the lowest melting point compared with an other main group element. Higher density, the density actually is higher than the main group element, right? And high electrical conductivity and thermal conductivity are variable because they are metals, and high tensile strength can hold a heavy load without breaking. So mostly we use the transition metal to do quite a lot of application, daily application. For example, you see airplane, we use titanium, a bit stronger metal. Nickel for the heating wire in the oven, copper, right? And lastly, using the vanadium be a material in tools. So therefore, the outermost shell of the transition metal have either one or two electrons. You can see mostly from the table, sometimes two, sometimes one in the outermost shell. But remember, why we put them in the transition metal? Why don't put them in group 2? Why don't put them in group 1? Because they are not losing one electron or two electrons. They are variable, okay, electron losing. So therefore, we cannot put in group 1, we cannot put them in group 2, something like that. Because of the similar outermost shell electron, so therefore, across the period, have similar chemical properties. Well, remember, for transition metal, it's across the period. But for the main group metals, is across the group. So therefore, across the group and across the period have similar chemical properties for transition metal. But for the main group metals, is across the group. So these chemical properties are also very different from those of the main group metals. Okay, if you remember, main group metal is across the group along. It's not actually, it's opposite to the transition metal. So in this chapter, we're going to talk about these three conditions. These three properties: formation of color irons, variable oxidation state, and catalytic properties. So first of all, we'll talk about class practice 49.1. Explain why transition metal usually have a higher melting point than metal in group 1 and group 2. Why? If you remember, in transition metal, electron in both the outermost shell and the next inner shell of electron will contribute to the C of the electron, so therefore they are stronger metallic bond, okay, because they have two shells to contribute to the C of electron. But in normally group 1, group 2, only outermost shell electron. So electrons in both the outermost shell and the next of more transition metals atom contribute to the C of electrons. Therefore, the metallic bond the metallic bond in transition metals are generally stronger. Okay. Explain why transition metals across the same period have the similar chemical properties, because they have the similar outer electron arrangement. Similar outer electron arrangement. So if you want to copy the answer, just stop the video, you can continue. Oh, next one, we are going to explain why they have a different color. So actually, transition metal have a different color. Some of them we learned already, like copper 2 is blue, right? Iron 2 is yellow, iron 3 is brown, something like that. Okay, we already learned some of the iron here, right? So therefore here we are going to talk about some of the, like simple iron. We know iron 2 and copper 2 why we have a polyatomic. Polyatomic means more than one atom. Like dichromy, manganese, but manganese is purple, dichromy is orange. Okay, for example, scandium and in aqueous are colorless, but some of them is colorless. Remember these two, Sc3 plus Zinc 2 plus we know you need to know, you need to memorize one of them. Scandium, Sc3 plus actually is colorless. Now you need to know. Main group, remember main group is colorless. Most of the main group are colorless. Only transition metal they have a color. Okay, you can see a titanium, Ti3 plus purple. Vanadium 2, violet. Vanadium 3 is green. So some students ask, do you need to memorize? Yes, you need to memorize the color. Sometimes they will ask in the multiple choice. Okay, so at least you need to know these transition metal, what is the color. But remember, main group element, group 1, group 2, group 3, they doesn't have any color. Dichromy, chromic 3 orange, chromic 3 green, Cl3 plus green to orange, we learn. You just memorize this one, yellow color. Chromium, CrO4, manganese, pink color, very pink, sometimes we say purple, sorry, colorless. Manganese 3 to black wall. MMO4 2 minus, that's green, but MMO4 minus purple. Be careful the color here. Manganese has so many different colors. Manganese and chromium, at least Cl3 plus Cl2O7 is the common. You need to know these two color. Okay. And manganese also, be careful. There's a 4 transition metal you need to. Iron 2, iron 3 we already memorized. Iron 2 green, iron 3 yellow. So I think here is already okay. And cobalt 2, you need to know pink color. Which one? Cobalt 2 chloride paper, if you remember. Alright. Why will be white to pink? Actually, because of this. This is the test. If you remember, this is a test of water exceed. If water exceed, cobalt 2 chloride paper will change to pink color. You do remember that? Blue to pink. Okay, because of these cobalt 2 actually is a pink color. Okay. Nickel 2 greener. Nickel, copper 2 we know, so you can see the one I highlight you need to memorize. Only copper, nickel. Rest of them actually is the old stuff. Here is the color. You can easily memorize. Class practice, copper 2, what is the color? Copper 2 blue, green, right? Iron 2 cobalt 2 nitrate pink 啦，in aqueous solution in solid state 咧 actually they don't have any color. Lithium to a green 啦，OK。Scandium 啦 ，orange 啦，大曲鎂啊嘛，大曲鎂 is orange。Potassium 曲鎂啫就 yellow 啦。Actually, they are very similar color. You need to memorize it. Oh, you need to memorize the color, and also they have a variable oxidation state. Now, for main group, they're only one. Okay, so that's why we can put them group 1, group 2. Group 1 is positive 1, group 2 is positive 2, group 3 positive 3. But for transition metal, actually they have more than one oxidation state. So therefore, we cannot put them in group 1, we cannot put them in group 2, we cannot put them in group 3. That's why you can see have a different nitrogen, the different oxidation state in nitrate and nitride. So therefore, these ions are polyatomic ion. Only one type of N3 minus and only one type of simple ion. Okay, but basically, many group elements, there's only one. Except the nitrogen. Nitrogen have more than one. Except nitrogen, but most of them basically they have more than one. So, but for transition metal, more than one, there are 2 or more simple cation. Okay, like iron 2, iron 3, copper. We have a copper 1, copper 2. Okay. So variable number of electrons can be removed from the outermost shell and the next inner shell, because this is the reason. Because transition metal, they are not only removed from the outermost shell electron, the next inner shell electron also donate electron to the sea of the electron, if you remember. So that's why they have a variable number of electrons. So hence they exhibit the variable oxidation state, just like potassium permanganate, MMO2, MM2O3, MMOSO4. You can see the transition is 76432, etc. Okay. So therefore, they have a variable oxidation state. Then you can see which one is more. You can see now manganese have 7 oxidation number, and the next more will be chromium and iron, and the next will 5. You can see less and less after that. Okay, only 2 ions have one variable. Be careful, one is zinc and the other one is Sc. If you remember, Sc positive 3 is colorless. This way is colorless. Zinc also colorless. Okay. Copper also have positive 3, but we are seldomly talk about this. So the blue color is the most common oxidation state of the element. Okay, most common fine. Okay, but they can be copper free. But copper free basically is not stable, but they can lose 3 electrons. You can see copper. Okay. After will be increased, so you can see the number of oxidation or transition from Sc to MM it increase, and after that decrease. Okay. Although transition, so the most of the oxidation number will be manganese. So although transition can exceed very oxidation states, but some of them are found to be more common than the other one. Yeah. Okay. So even they have so many chances to form the ions, but we choose the common one. But you can see iron mostly, iron 2 and iron 3. Even iron we have a positive 6, but seldomly is 5, positive 4, positive 5, positive 8. Mostly you can see in the compound is positive 2 and positive 3. Iron 2, iron 3. We don't have iron. We don't not common to see iron 4, iron 5, iron 6. And the manganese also 2, 4, 7 are the more common one. Okay. So transition actually more than one oxidation state, but they have some common one, but not all of them are common. Metal ion in high oxidation tends to as a oxidizing agent, but low oxidation state we call them reducing agents. Okay, reducing agent. we need to check the oxidation state. Okay, so for example, iron 2 and 3. So based on the result, high oxidation state will be oxidizing agent. So therefore, positive 3 mostly will become an oxidizing agent. Okay, so generally you can see iron 3 more stable than iron 2. However, they are interconvert to each other. Iron 3 can change to iron 2, iron 2 changes to iron 3. So iron 2 can be oxidized to iron 3 because they're doing oxidation, and then iron 3 do reduction back to the iron 2. So you can see mostly. But how can we make iron 2? When iron put into the acid, we can form iron 2. Okay, but iron 2 to iron 3, iron 3 to iron 2 actually is a redox reaction. Okay, they can be a reducing agent, or in the presence of oxidizing agent, iron 2 will be changed to iron 3. Iron 2 is a reducing agent. Okay, iron 2 is a reducing agent. Why? Because the low oxidation state will be the reducing agent. So this can be a reducing agent, means it can do the oxidation. So iron 2 doing oxidation, they will change to iron 3. Okay, just like iron 2 reduce chlorine will be the oxidizing agent. This is the redox. I don't go through in detail. And this is the result. Okay. And also on the other hand, iron 3 can be an oxidizing agent. Oxidizing agent means they will do a reduction. Okay, so therefore you can see they're doing the reduction like this. And on the other hand, the copper will doing the reducing agent by doing the oxidation. Okay. So overall equation will be like this. Well, manganese, you remember permanganate actually is oxidizing agent. Why? Now you know now, because the oxidation state is positive 7. So permanganate is oxidizing agent. So you see permanganate is an oxidizing agent because of high oxidation state. In acidic, remember, in acidic usually reduced by the reducing agent. Okay, remember in acidic, okay, if there's not acidic, permanganate will not be the oxidizing agent. Okay, and then reduce, I don't go through in detail, you can do it by yourself here. Okay, and also in alkali, we didn't talk about. In alkali, they will form manganese 4 oxide. In alkali, so you can see in different environments, they can be a different product form. In acidic, they will form MM2 plus, but in alkali, be careful. In alkali, they will form MMO2. Okay, so the MMO4 change to MMO2, and then in alkali environments, you can do this by yourself. How to make this equation? Okay, we learned already. Okay, now I do it here again. How to make this equation? Because this is in alkali environment. How to rewrite the half equation? Firstly, we need to memorize that in alkali environment, permanganate will change to MMO2. And then now we are balancing the water. 2 oxygen 4, and then here will be 4H plus. As I mentioned, because in this case, this is the 4 plus, this is a 3 minus. But as you remember, this is an alkaline environment. But now I'm doing in acidic, so I need to eliminate the H plus. So both sides I need to add 4 hydroxide. So therefore, after I add 4 hydroxide, here will become 4 water plus permanganate equal to MMO2 plus 2 water and plus 4 hydroxide. So this one 2 water, but here 4 water, so therefore these 2 water eliminate. After that, here become 2. That's why you can make the equation from the textbook here. Okay. remember we're using this method. Okay, we firstly using the old step by balancing the H plus. After that, check the environment. If the environment is alkaline environment, you just add the hydroxide in the both side, then you can eliminate the H plus by ourselves. Okay, so this is the color change. I don't go for that. Like you say manganese 4 oxide. Basically, what is the color? Brown precipitate. Okay, brown solid. Actually, MMO2 cannot dissolve in water. Okay. What's color practice? Iron has various oxidation state. The lowest oxidation state of iron appear in iron 2 chloride. What is the oxidation number of iron in iron 2? More obviously, iron 2, so therefore the oxidation number is positive 2. The most stable will be positive 3. Okay, iron 3 is a stable one. Okay. When aqueous bromine was added to iron 2 chloride, the solution changed from pale green to pale yellow. State the chemical species form that give the pale yellow. The pale yellow, of course, the iron 3 plus. Iron 3 plus is pale yellow, very brown color. Okay. Write down the equation will be iron 2 plus bromine change to iron 2, change to iron 3. So it is 2 plus 2 bromine. Okay. So if you don't know how to write this equation, you try to write 2 half equation by yourself and then combine them together. Actually, you can form this equation. Explain why MMO2 can be an oxidizing agent or reducing agent. If you remember, MMO2, the manganese, the oxidation number is positive 4. It can be reduced to positive 2 or positive 3, right? Or it can increase to positive 5 to positive 6 or positive 7. So therefore, MMO2 is in the center. It can be an oxidizing agent. It can be reduced to positive 2, positive 3. Now let me write down here. The oxidation number of manganese is positive 4 in MMO2. It can be reduced to positive 2 or positive 3. Sorry. Okay, just like oxidizing agents, or increased to positive 5, positive 6 or positive 7. It would be a reducing agent. Catalytic properties of the transition metal and their compounds. Actually, for the transition metal, they can be a catalyst. Okay, but how can they change the rates of the reaction without being used up? Okay, never use up. They didn't use up. They just change the rates of the reaction. Okay, remember, they just change they speed up can be speed up, can be slow down the reaction. Okay, but mostly, why do people using catalysts? Because they want to speed up the reaction. Okay, this is the reason why they are using the catalysts. Okay, but using the catalyst actually does not being used. Okay, they just like a helper. Okay, to speed up the reaction. So mostly often use the catalyst in the industrial and chemical process. During the the transition metal and compound usually form an intermediate compound. Okay, and then later on they will regenerate. So that's why they doesn't use up. Just like let us consider the iodide together with the p-oxide disulfide. Basically, this reaction normally is very low process, but very slow at the room temperature. Okay, because because you can see these two ions is negative charge ion. They are not easily react to each other. Okay, but if we add the catalyst is iron 2 or iron 3, then the reaction can be speed up because iron 2 iron 3 is a positively charged ion. They will attract to each. You can see it. Firstly, iron 3 will attract the iodine to become iron 2, and then later on iron 2 will react with the S2O8 and then to form another compound. So iron 3 will be coming out. Okay, so as I mentioned, iron 2 can change the iron 3 back to the iron 2. So it seems that it doesn't use. Okay, but the reaction we finally get the one, and it can be speed up. So this is the very useful of the transistor metal. On the other hand, if iron 2 are added, simply take place in different order. Iron 2 back to iron 3 back to iron 2, just like that. So again, therefore iron 3 iron 2 mostly can be a catalyst because they can interconvention between these two. Okay. So therefore you can see the transition metal just like this. Okay. Finally, divine ion in the Haber process, just like this. Haber process, basically, what is it? Haber process is the process to form the ammonia. Okay, to form the ammonia. Okay, so between the nitrogen and hydrogen react to each other. Okay, by using the finely divine iron as a catalyst. Okay, so you need to memorize this reaction because later on we need to talk about this Haber process. How can we use it? And the vanadium oxide is used for making the sulfuric acid. Highlight here. Sulfuric acid is using this one, catalyst. You need to memorize the name of the catalyst. Platinum, I don't talk about this. Okay, catalytic converter, platinum, rhodium. I don't talk about this. You can go through in detail. You can read it at home by yourself. And there's some example. Okay, for example, for hydrogen peroxide H2O2 decomposition to change to water and oxygen by using the MMO2. Okay, also like this. It can be a catalyst. And then TiCl4 titanium 4 chloride. Okay, by using the polymerization. This is the example you can read it. Also example, okay, you can read why they can be mostly commonly used as a catalyst. Vanadium 4 oxide is used as catalyst in the manufacture of sulfur trioxide in the contact process. The reaction proceeds in two stages, as shown below. Why the vanadium 5 oxide used in powder form in the reaction? Okay, why actually to increase? Why they're using powder to increase the surface area? Of V2O5, so that more active sites are available for the reaction. Why vanadium 5 oxide considered as catalyst if oxygen is not added to the reaction mixture? Because if you don't, it cannot be regenerated in the absence of oxygen. A catalyst must not be consumed in the reaction. Okay, so therefore, that's why if oxygen is not added, so the catalyst must not be consumed in the reaction. it cannot be regenerated. So catalyst reaction is fine to proceed in two stage. Write the overall ionic equation. Actually just cross out the similar stuff alright. And then finally you will find ClO minus and then 4 hydroxide here. So in two stage. So you need to balancing equation because I need to eliminate some of the compound. For example, here 4, right? But here 2, so this equation times 2. After times 2, the left behind will be this one. Deduce which chemical species is likely to be the catalyst. Which one? You delete COOH2, so this one will be the catalyst. Describe the action of catalyst. You stay in B. You will reduce to COOH2 reduce ClO minus to Cl minus, and itself is oxidized. Okay. So important of the transition metal, there's some daily use and also their compound. Actually you can read here, you just like from free stuff. I don't talk about in detail. Okay, you can read it at home and just like the common sense. Okay, this way make of brass suggests two major transition metal. Brass actually is a copper. You do know what? Copper and zinc. Copper and zinc. Okay, just suggest one other use for each metal in A. In each case, suggest suitable properties. Like for example, I don't write a copper. What is the use? Electric cables or electrical wires. Because why? Good electrical conductivity. Electrical conductivity. Alright. How about zinc? Graphite, right? Graphite iron. Because since zinc is higher reactive than iron. Okay, you can protect. You can protect iron. Okay. So that's the end of the chapter 49. This is quite easy chapter, easily to study. Okay, if you have any problem, please come to me. Bye bye.